Unit 3 is about the periodic table, elements, and compounds, and how to name ionic and covalent compounds. We're going to start with the periodic table. Before we get into what's on the table that we know today, let's talk about where it came from. The first person to compile a list of all known elements was a French guy, Antoine Lavoisier. This was in the 1700s. Now, he knew 33 elements at the time. Keep in mind that when he's doing this, he's doing it before John Dalton proposed the atomic theory, which was in 1803. Okay, so we knew that elements existed before we knew atoms existed. So he's probably finding the most common ones, right? Oxygen, hydrogen, iron, things that are very easy and very plentiful. So we make up a list of 33 of those. Okay, those are the first 33, and the first person to compile the list was in the 1700s. John Newlands, so this is now after John Dalton's atomic theory, proposes an organization scheme in 1864 called the Law of Octaves. So what he did is he realized every eighth element seemed to have some repeating patterns, some repeating properties. And so he called this the law of octaves. Any of you musicians out there know that an octave makes the same note just at a higher or lower pitch. So you notice every 8 elements, there was some sort of repetition there. It didn't work for all elements, though, but he was beginning to see some periodicities, some repeating properties. So John Newlands, an English guy, was the second one. The real breakthrough in the periodic table came with these two guys, Lothar Meyer, a German guy, and Dmitry Mendeleev, a Russian. Really, Mendeleev ends up getting more credit for this. They both were working independently, so they didn't know of each other's work. But historically speaking, most people call it Mendeleevs Table, not Meyer's Table. But in 1869, so this is just shortly after the U.S. Civil War, just to give you some time frames here. Each of these guys finds a relationship between atomic mass and properties. Now, again, we don't know what protons are. We're talking about 1869, so we don't know what protons are or what neutrons are, but we had relative masses. We could still figure out the relative mass of things even way before those points, okay, well back then. So they could arrange things by relative masses, and they did it by atomic mass. Obviously, we don't know what protons and neutrons are at this point. Okay, but what they noticed is that there were some repeating patterns, and this is lined up not by atomic number, but by relative mass here. So if you look here, this table, hydrogen, lithium, sodium, apparently copper, silver, gold, all seem to have some similar properties. So they put them in left to right, not top to bottom like we're used to seeing now. Okay, but notice there's some gaps in here, all right? Something between molybdenum and ruthenium there. So we didn't have everything. However, the huge advantage to this table, and I'll write it down because this is a good future quiz or test questions, is that it allows us to predict elements not yet discovered. Okay? So it made some predictions about, hey, there's some gaps in here of things that we might not have yet. All right, that was the huge advantage here to getting this table for the first time. It wasn't perfect. There were still some inconsistencies because we're not going by number of protons, the atomic number, because we didn't know what those were yet. But in general, this was a huge step forward, allowing us to predict where some elements should be so we knew where to go looking for them. And sort of the final piece to this, putting things in the order they are today, was done by Henry Moseley, an English guy. Didn't live too long, 1887 to 1915, if you notice that date there. He died in the First World War. So Henry Moseley arranged elements based on the number of protons. So finally they're in order of atomic number. So this was 1912, 1913, shortly before the First World War broke out. So it's kind of a shame we lost him as a scientist to that. Because remember, Rutherford's experiment on protons was done in 1911, so that's the very earliest anyone could have possibly ordered them by protons. But he's the first one to do that. And as soon as he does, all the inconsistencies of Mendeleevs Table and Newland's law of octaves go away, and we see that clear order of properties, or of repeating properties. And this leads to what we call the periodic law. There's a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number. So when we put them in number of protons in order, we see repeating patterns. Okay, that's why it's called the periodic table. You wonder why it's called the periodic table? Well, if something happens periodically, it happens every so often on a predictable fashion. So we call it the periodic table because the patterns, the properties repeat every so often. So that's why it's called the periodic table. Okay, so talking about the arrangement of this thing, I've got pictures of this all over the place for the next few slides. So if you've got yours, you can try to follow along and see exactly where we're looking. The arrangement, so the columns up and down, all right? Those are called families. Sometimes they're called groups. Groups or families. You'll hear me say either one. You've got your groups 1A and 2A here, and then 3A through 8A over here. 1A is the first column, 2A is the second column, 3A is the first column here, 4A is the second column, and 8A is the one all the way out over here, right? You guys can figure that out. All right. We consider those the main group elements. And for the most part, when we're dealing with stuff this year, we're dealing with main group elements. Every once in a while, we'll get some transition elements. It's very rare that we'll deal with any of this stuff down here on the bottom. All right. Here in the middle are these B group elements. So these are the A group elements on the outside. Here in the middle are the B group elements. These are the transition elements. Okay, they transition you from one side of the table to the other. All right. So the columns are called families or groups. We have the A families and then the B families, main group elements, transition elements. The rows are called periods. So from left to right is called a period. We have 7 periods. Okay, and as you can guess, when you begin a new column, that's when the patterns start to repeat. Okay. Elements may be classified as metals, nonmetals, or metalloids. All right, and we'll show you where those are on the table here in just a moment. Okay, so metals. Most of the periodic table is metals. Metals are shiny when they're smooth and clean. They're generally solids at room temperature. The only exception to that would be mercury, which is element 80. Okay, and they're good conductors of heat and electricity. They're malleable and ductile. And so where are they on the table? So the staircase line over here, and I drew it in, and hopefully the table that you've downloaded or that you have on your browser has a very clear line in here. If it doesn't, draw yourself one in. Elements that are along this line are considered metalloids, with the exception of aluminum. Aluminum's a metal, but boron, silicon, germanium, arsenic, antimony, tellurium, polonium, okay, all those are considered metalloids. Everything else, beginning here with aluminum, gallium, tin, bismuth, okay, and these elements down here are basically existing only for fractions of a second, so we don't really deal with them a whole lot. But everything from here over to the left, right, everything from there over, okay, all the way, now with the only exception here of hydrogen, which is a non-metal, which would end up on that side. But everything else on that side of the table is a metal. Okay, so from lithium on down, all right, lawrencium, all this stuff we consider a metal. So let's talk about some specific groups within the metals. Okay, this first column here, with the exception of hydrogen, it's column 1A, family 1A, group 1A. And we're considering everything here except for hydrogen, because hydrogen's not a metal. We call this family is a special name, not just the 1A family. We call this the alkali metals. So lithium, sodium, potassium, rubidium, cesium, francium, these are the 1A metals. These metals are extremely reactive as elements. Okay, there's a lot of stuff made out of them, right? Table salt is made out of sodium chloride, but it's already reacted, so it's not dangerous anymore. But by itself, these things are extremely reactive. And because of that, it's very rare to find these just naturally occurring. Odds are, in the 4.5 billion years that Earth has existed, if there was any sort of, supply of that available, it's probably already reacted. Okay, so you're not going to accidentally start digging in the ground and find a hunk of potassium metal. It doesn't work like that. Okay, these things are probably already in compounds. We can refine them out of compounds and get them. We have some lithium, sodium, and potassium in our stock room. So you can get them. You have to, make them chemically. Basically, have to get it out of a compound. But in nature, they're pretty much all reacted. So you're not going to accidentally encounter it here. Something to note about them is they are very soft. It's kind of weird. Like, these are metals. This is a dull knife here. And I've cut through lithium, sodium, and potassium before. Lithium's actually the hardest of the bunch, but like potassium, you can use like a plastic blade to cut through that. Sodium, same thing. It's kind of like trying to cut through softened butter. is sort of, if I had to liken it to something. But they're very, very soft, which is not what you normally think of when you think of metals. You think of, titanium and iron, these really strong things. Well, these metals are actually pretty soft. You can cut through them with a dull knife. Okay, our second family here, so the second column, family 2A, group 2A, also has a special name. So not every family has a special name. This one does. This is called the alkaline earth metals. So that's beryllium all the way down to radium there. These metals are also reactive. I think I forgot to mention this on the previous slide, but 1A metals tend to form +1 charges, and 2A metals tend to form +2 charges. Okay? They're also reactive. They're not as reactive as 1A metals. Okay, 1A metals are the most reactive metals here. But you still don't want to, touch these things for too long. They are going to react. Again, this would be pretty rare to go out and just find these things in nature unreacted. Okay, you'd have to refine them out of something. An interesting one that I always like to point out is calcium. Element 20 there. When you think of calcium, your brain goes to dairy products, and it looks white like milk or yogurt or ice cream or something like that. And calcium is actually a metal. The calcium that's in the milk and dairy products, it's actually a calcium ion. That's usually what you're looking for, and that's why it looks white colored. But calcium, unreacted calcium, is a metal. It looks like this. It's kind of interesting. You always think of it as this white-colored substance. Well, after it's reacted, it often turns into a white-colored substance. But before that, it's actually a shiny metal. So here it is inside of a tube that's basically been vacuum sealed so that there's not going to be any oxygen reacting with this, so it'll maintain its shine. So you can actually see what it looks like. Pretty cool. We have some calcium in our stock room as well. So maybe if we get a chance, we'll get to pull that out and look at it. Okay, so what do we have left? We need to talk about the nonmetals. So that's going to be the upper right of the periodic table plus hydrogen. Remember earlier we said hydrogen's kind of on its own over here. So again, we're ignoring the stuff that's along the staircase line because that is considered a metalloid. So everything to the right of it, though, from carbon all the way over here, right, phosphorus, selenium, okay, iodine, all the rest of that stuff to the right of it, plus of course, hydrogen here is considered a non-metal. These are usually gases, so non-metals, or brittle or dull solids. Phosphorus is a dull solid. Sulfur is a dull solid. They're poor conductors of heat and electricity. The only liquid of this group is bromine. Okay, element 35 right there. Okay. And then there's a family here within the non-metal category that's got a special name. It's called the halogens. It's family 7A, so it's the second from the right, family 7A. These are extremely reactive, so much like, family 1A over here, family 7A is also extremely reactive. They tend to form -1 charges. These include fluorine, chlorine, bromine, iodine, astatine exists a little bit. It's often radioactive, so it doesn't exist for too long. But these are extremely reactive. Here you got a flask full of chlorine. You would not want to breathe this in. That would do a number on you, probably kill you. They're very, very reactive. We have some bromine at school. We have some iodine at school. We can't keep the other two. We've made chlorine gas before as part of a demo. Fluorine is just too dangerous for us to even try to mess with. There's no way to really seal that thing in a container very well. Plus, it's just extremely reactive. So we don't mess with that one. Or it's not calcium. Last group to talk about here as far as special naming goes. The one all the way over here to the right, family or group 8A. Okay, these are called the noble gases. These are non-reactive. So family 8A does not react with stuff. It stays as that particular element. Oftentimes these are used in neon signs. So neon is element 10, right? When you put that into a neon sign, it turns kind of that neon orange color. But other ones make colors too. Here's argon, kind of makes a blue color. Helium, I think, makes a yellow color, if my brain remembers that correctly. But they're generally non-reactive. Under some extreme circumstances, you can get xenon to do some stuff. But other than that, they're non-reactive. An important kind of side note here is that these were some of the last elements to be discovered. And if you stop and think about why that is, Well, there's two things going against it. Number one, they're non-reactive. How do we know that atoms and elements exist? Well, it's because we were able to check that they reacted. That's how John Dalton figured that stuff out. Not necessarily that you could see the atoms, but you knew that they were doing something because they were reacting with something. Well, these don't do anything. And then number two, they're all gases, so they're invisible. So it's not like a piece of metal that's non-reactive. These are gases that are non-reactive. So these were some of the last elements to be discovered because we had to actually kind of basically refine them out of just atmospheric gas. Is what we ended up having to do there to try to fill in the last gaps of the periodic table. So kind of a cool group of elements. If we get a chance later in the year, we might see some of these lit up as neon signs, and we'll talk about why it actually lights up like this. Okay, there's a special effect that's causing this. Okay, so we talked about metals, we've talked about nonmetals. Let's talk about the guys on the line here, the metalloids. All right, so these are the elements that are lining the staircase on the table, with the exception of aluminum. Aluminum is considered a metal, but everything else that's on that line is considered a metalloid. They have properties of both metals and nonmetals. There's many different uses and properties of these, and you can take advantage of the fact that it kind of behaves like a metal or kind of behaves like a nonmetal. A good example here is silicon. Silicon is used in computer chips and human prosthetics. An advantage of silicon, and like why is it chosen, and germanium is used in a lot of computer chips as well. What's the advantage there? Well, being a metalloid, it's kind of got a lower melting point. Some of these metals have really high melting points. Okay, it's hard to liquefy the metals. But then the nonmetals obviously have very low melting points because they're nonmetals. Right there, a lot of them are gases, ones up here, or liquids in the case of bromine. But something like silicon or germanium has a low melting point, and it's also a decently good conductor. So we use them in computer chips because you can melt them and put them in specific places, and it will still conduct. So it's kind of a useful little tool there. So anyways, there are the metalloids.